announcements. One is that there are the conference dinner today is at the Israeli Museum at the restaurant there, and there is a map outside. It's a very short walk from here, about 10 to 15 minutes.
From here?
From here. Depends on how fast. 5 run. There's a map outside and also small maps on the registration desk downstairs if somebody wants to take them, but it's very easy to get there. And I strongly recommend people just walk around the museum. It's very nice. You can just go there sometime before that and walk around the museum. So that's one thing. And the second thing is there will be a group photo today after the third talk. So I asked everyone not after Tim's talk, after the talk after Tim's talk, after the third talk we all meet downstairs just outside the building and
Okay. So now Tim Austin is going to lecture on additivity properties of Sofic entropy of measure on modules.
Okay, right, thank you very much. Let me first say that it is a great privilege to be able to come and contribute to the respects being paid to this institution and to Hillel. I know that it and he have both been enormously influential on my mathematical life, and so it's nice to be able to give something back in this setting. Although perhaps I shouldn't say that to have actually given the talk. All right, so this is another Sofic entropy talk, and happily you've already heard two definitions, or rather you've already heard the definition twice of Sofic entropy in this conference. But firstly, I use notation that's a little bit different, and I can't switch over in my head, it's too difficult. And secondly, I have a voice in my mind saying, don't feel bad about telling the audience things they've already heard. I'm pretty sure it's Benji's voice. So I'm going to give you a definition again. I'm going to start with the definition of Sofic group, which is basically the same thing that Lewis wrote before, and then I'll go to the definition of Sofic entropy, and then my talk will be in some ways a natural continuation of Lewis's, but I'm going to talk about a different problem that he didn't mention. Okay, so let's just remind ourselves what a Sofic group is. I wrote the definition here. So a group is Sofic if it has one of these. This is the same thing that Lewis wrote before. So it's a sequence of maps from the group to the symmetric groups of some finite sets. Typically, you should think of the sets as having size tending to infinity, with two properties. Firstly, it looks more and more like a sequence of homomorphisms at individual vertices. So this says if you look at the vertices in Vn, and then for two fixed group elements G and H, you look at the subset of those vertices where the group law is respected for the action at that vertex V, then this is most of the vertices once n is large. Okay, so a nice way of saying that comes from finite discrete probability is we say the group law holds with high probability in V as n tends to infinity. So when I write WHP, it means with high probability. Okay, so for each G and H separately, we're saying the group law holds for the action at V with high probability in V. This is absolutely not the same as saying this holds for all G and H with high probability. Right, that would be a lot stronger. But for each G and H that you choose, this starts happening more and more. And then the second thing is that the action starts to look more and more free. So if G is not the identity element, then its action at a vertex V seems to move V non-trivially with high probability in V. Okay, so that's the definition. Let me draw the sort of picture that goes with it. So you might like to imagine this when G is finitely generated, and let's imagine this when G is actually a free group, say on two generators. Then there's a corresponding Cayley graph. It's just a tree. So this goes on and so on. And on the other side, you have the sequence of finite sets Vn. We draw that as some kind of blob. And now for a given vertex in Vn, the actions of the group elements move the vertex around. They don't necessarily have to respect the group law, but they move the vertex around. And so you can ask about the action of the two generators. And those are going to draw some kind of graph on Vn, where each edge is labeled by the generator that gave you that edge. So perhaps if that's A and that's B, maybe sigma n of A moves V over here. So that directed edge would be labeled by an A, and then sigma n of B moves it over here. And then they also came from somewhere. And so on. And so the rules for a Sofic approximation basically say that for any finite patch in the group, once n is large, most vertices see an exact copy of that patch around them. So this graph looks like the Cayley graph of the group up to some finite radius around most vertices of V. So in the special case of the free group, the Cayley graph is a tree, and these are what are called locally tree-like graphs. It's a sequence of locally tree-like graphs. Does that make sense? Okay, so this is a nice way of visualizing a Sofic approximation. So now let's suppose we have a Sofic group. We're going to fix that for now. And also we'll fix the Sofic approximation sigma. And as Lewis said, basically everything I do will depend on sigma, although it's not completely clear how much dependence there is, but we know there is some, and I'll say more about that later. And now I'm going to study probability-preserving actions of G as well. To make my life easier, I'm just going to look at shift systems. So I'm going to suppose that I have some shift invariant measure mu on the space A to the G, where A is a finite alphabet. And S is the shift action. And if you ask me which shift action, left or right, I'll tell you the wrong answer, so don't ask me. Okay. So I'm going to study systems like this. Of course, this is not completely general, but you can make it completely general if you allow A to be something like the unit interval. If you allow a slightly more general class of alphabet, then any G system is isomorphic to one of these. And you can actually extend everything I'm about to say, with one exception, to that case. So this is a more general story, but I'm sticking to a finite alphabet for simplicity. And of course, it will be a very important part of the story that the invariants I end up defining don't depend on the shift system except up to isomorphism. So if you have some abstract system, you can define its Sofic entropy, say, by choosing an isomorphism to a shift system, and then the answer is not ambiguous. All right, so let me just go over very quickly again the definition of Sofic entropy. So I need a couple other definitions first. So the idea is to approximate the shift system with this measure by data built over these finite sets Vn. So first of all, let's suppose we have an element of A to the Vn. Now, if I'm being careful, I'll try and remember to write elements of A to the Vn as a bold letter to tell you that that's what they are. And let's also fix a vertex in Vn and a finite window in the group. Okay. So now I've told you that once n is large, you have your finite patch, your finite window W in the group. Then there's a corresponding window around most vertices that's a copy of the Cayley graph restricted to that window. And A is a coloring of Vn by elements of this alphabet. So for any of those copies of W, you can restrict A to that copy of W and get a coloring of W. Okay, so let me give that a name. I'm going to call that the pullback at V of A. So in notation, that's just this guy. So you look at where V gets moved to by W, you take the colors given to those points by A and pull them back to W itself. Okay, so that's the pullback of A at V. All right. And now we regard a coloring as a kind of approximation to mu itself if the following happens. As you move V around, you're seeing all these different copies of W centered at different points in Vn. And you can ask with what frequency you see different colorings of W arising from that single big coloring. And the coloring is an approximation to mu if those frequencies are given roughly by mu itself. So that's a kind of equidistribution. Okay, so where's the thing? So a nice way to say this is to define the empirical distribution of A which I'm going to write P sigma n W of A as the following. You simply take an average over all elements of Vn of the delta mass at that pulled back coloring of W. So this is simply the measure that tells you with what frequency different colorings of W appeared as you move that copies of that window around in Vn. Okay, and then we say that if O is a weak star neighborhood of uw, that's the marginal of mu on this finite set, then A is an O-good model mu if its empirical distribution is in that neighborhood. So it's close to mu itself in the sense of being in this neighborhood. Okay? So that's asserting some kind of equidistribution relative to the measure mu. Does that make sense? Sorry? No, so, yeah, again, this is exactly the same thing I should have learned from Lewis's talk. So here I'm picking an n, right? I'm looking at an element, one element of a to the vn. It has an empirical distribution, and it is an O-good model for this same fixed value of n if its empirical distribution lies in O. And now if you want to be economical with notation, you can actually ignore W, right? I can make this definition for the whole of G if I want to. That sort of feels a bit worrisome, right? Because now you have this infinite group and a finite set Vn, so the group is being wrapped around the finite set infinitely many times, and you're pulling back the whole coloring. But you have to sort of keep in the back of your mind, you only really care about what it looked like locally. I'm just not writing the window anymore. And so over here, I can write an empirical distribution where I ignore the W. So that's now a probability measure on the whole of A to the G. But again, I only really care about its marginal locally. I'm just not specifying how locally anymore. And now again, you pick a weak star neighborhood now of mu itself, and you say that A is an O-good model of mu if its empirical distribution is in the weak star neighborhood. And this doesn't really change anything because in the weak star topology, there will be a finite window such that the weak star neighborhood only cares what happens in that finite window. So really, I can hide the choice of W inside this O, and that makes the notation shorter. Okay, does that make sense? Is that confusing? Okay, so that's an empirical distribution and what it means to be a good model. And so now to define the Sofic entropy, we're going to count good models. So let's give a name to the set of these. Let's call it omega. So omega of O comma sigma n is just the set of models which are good in this sense. Okay, so these are the ones that have some equidistribution in this sense relative to mu. And now I define the Sofic entropy of my shift invariant measure mu relative to sigma to be the following. So this is basically the formula that Lewis had before, except that in Lewis's formalism, he doesn't restrict to a shift space to begin with. He has some arbitrary action on a compact metric space, and then he has to worry about maps that are approximately equivariant and build that into the definition of a good model. That's the principal difference. Here I'm not worrying about that because I'm just taking single colors from my coloring in the shift space.
So this is hardly depends on choice of approximation.
This does depend on the choice of approximation. Yeah, so this is going to give you the same numbers as Lewis's definition, and it will be different for the sigmas in just the same way that his was. It does depend, and we'll see more of that later. All right, so let's just say one word about why this is a natural thing to do. So there's a couple of obvious sources of examples of Sofic groups. I mean, there are a lot of Sofic groups in the world, and we don't know whether all groups are actually Sofic. But a couple of large classes are the residually finite groups. They're especially easy because then you can take the sigma n's to actually be true homomorphisms. They're true representations by permutations of finite sets. And the other obvious class of examples is amenable groups, because there you can take a Fulner sequence in the group itself to be your sets Vn. If you have a Fulner sequence, then if you fix a group element G, then once n is very large, for most points in the Fulner sequence, its translate by G will still be in the Fulner sequence. So then once n is large, you define sigma n of G to be that translate if it makes sense. And if you fall over the edge, then do something arbitrary, because that doesn't happen very often, so you don't care. Okay, so Fulner sequences give you Sofic approximations. And in the case of a Fulner sequence, what's going on here, up to little o errors that don't matter in the definition, is that you're taking a coloring of a very big Fulner set, and then inside it, you're moving this smaller window around, and you're asking, with what frequency do you see different colorings of that smaller window inside the name, the coloring of your big Fulner set? And then the good models are the ones where you see roughly the right frequencies. So that's a very classical thing. That's just called a typical word as far as the frequencies are concerned. And we know that if you draw the coloring from mu itself, then it will have that property with high probability. That's just the ergodic theorem. So if mu is ergodic, then it will have that property with high probability. And so good models give you an approximation to the support of mu itself over the Fulner set. Most choices of coloring from mu will give you the right empirical distribution. And actually, if you count good models in that sense, you're basically counting typical sequences, and it's a classical fact that's the same thing as estimating the entropy. That's a consequence of the Shannon-Macmillan theorem. So this definition where you're looking at equidistributed colorings really just generalizes this observation from the Shannon-Macmillan theorem that entropy is counting how many typical colorings are there for the measure mu on a Fellner set. Okay. So, good. Let me see if that's enough of that for now. Yes. Okay, so a couple of things I want to mention. Let me say again, this does depend on sigma in general, and I will show you more examples of that later on, but it is an isomorphism. For each given sigma, this is an isomorphism invariant of the system. So if you have two isomorphic shift systems, then these will give you the same number. So this is somehow the analog of the Kolmogorov-Sinai theorem. And if you define all this in Lewis's way using metrics on spaces, this is kind of the analog of saying that it doesn't depend on the choice of metric. Saying it doesn't depend on the choice of generating partition is the analog of saying it doesn't depend on the choice of the metric. But this is a sort of more classical way of saying it. Okay, so this is the Sofic entropy, and this is a substitute for Kolmogorov-Sinai entropy when the group is non-amenable, and you can use it to generalize many of the classical theorems from the world of Kolmogorov-Sinai entropy beyond amenable groups, the obvious one being the classification of Bernoulli shifts. I understand why Lewis introduced this in the first place. But in other ways, this entropy does not behave as well or as regularly as Kolmogorov-Sinai entropy. The first obvious thing is that it does depend on sigma, so that's an added layer of complexity. The next thing is that it's not monotone under factor maps, as Lewis said. Even though it's isomorphism invariant, it loses the property of monotonicity under factor maps. And what I want to focus on today is another property which doesn't work so simply for this guy as for Kolmogorov-Sinai entropy, and that's what happens for Cartesian products. So the question, is it true that H sigma of a Cartesian product of two, and I'm working just with shift systems, so mu is one shift invariant measure for one alphabet, nu is a shift invariant measure for a different alphabet. Is it true that the Sofic entropy of the Cartesian product is equal to the sum of the two Sofic entropies? Okay, let me tell you right away, the answer is no in general. But the real question is, what can we do instead, and what can we say about when and why this fails? And that's what my talk is going to be about. Okay, so the questions at this point before I go on with that. All right, so the plan is, first I want to tell you why you might think this is true. And then I'm going to tell you the obvious, stupid, irritating reason why it cannot be true. And then I'm going to give you a cheap way of removing that reason. So then you might hope that it's true. And then I'll give you an interesting reason why it's still not true. And then I'll actually fix it. Sorry? Oh, no, I'm fixing sigma. I'm fixing sigma. Yeah, so they will be for some. That's a corollary of things that come later. Yeah. So given sigma. And the issue of choosing the right Sofic approximation is important, and that will show up already in the irritating stupid reason. Okay, so let's just say something quickly about why you might hope this is true, and why you can actually get half the answer pretty easily. So let's just go back to the definition. For mu times nu, what are we doing? We're saying, well, let's suppose n is a weak star neighborhood.
So wait, one inequality should be off.
Yeah, I'm just getting to that. Suppose n is a weak star neighborhood of mu times nu, and you want to estimate the number of good models for the product measure, so models whose empirical distribution is in n. So you look at omega of n sigma n, that's the pairs AB in a to the Vn times b to the Vn, such that their empirical distribution is in n. Okay, so the first thing, and this is exactly what you were saying, is that if you have something whose empirical distribution for the whole pair is a good model for mu times nu, then A by itself had better be a good model for mu, and B by itself had better be a good model for nu. Okay? So let me write that formally. For any weak star neighborhoods O1 of mu and O2 of nu, there is an n such that this is contained in the set of pairs of O1 good models for mu and O2 good models for nu. Okay? If you're a good model for the product distribution, then the two coordinates had better be good models for the marginals. So that's easy, and that gives you one direction, because now this is at most the product of these. You take logarithms and it becomes a sum, and that's subadditivity. So subadditivity is true, and actually subadditivity is true for any joining of mu and nu, not just the product. So that's the easy direction. For any lambda adjoining of mu and nu. Okay. And now why might this make you think, for the product measure, perhaps I get an equality? Well, it seems that all you need is that if you take a typical good model for mu and a typical good model for nu and just put them together, maybe that's a good model for the product. And that is drastically false in general. And that's why this can fail. So let me give you the first really irritating reason why it's false.
What is this J?
That's the set of joinings of mu and nu. Okay, so stupid reason for failure. Well, the thing is, in this definition, I took a lim sup along subsequences, right? And what could happen is that for mu, there's one subsequence where you're getting some good models, and for nu, there's a different subsequence, but actually they're disjoint. So there just is no value of n, so that you're seeing good models of both measures along those vn's. Right, could have. So let me write it like this. I could have that this is converging to the Sofic entropy of mu along some subsequence, n1 less than n2. And the same for mu. So similarly, for h sigma nu along, say, n1 prime, n2 prime. But I can't do this with the subsequences intersecting infinitely often. And in that case, it's all going to fall apart, because I can't find values of n where there are good models for both. So, but subsequences disjoint. Okay. So in that case, you'll just find that for very large n, is always one of these is non-zero, but the other one is 0. And so this is always 0. So what you're picking up is a minus infinity for the Sofic entropy of mu times mu, because it's log of 0. But for the others, you're getting two positive values because of those two different subsequences. All right, so that's somehow not an interesting problem. So what we should do is, of course, choose a better Sofic approximation that does away with it. Okay, and what I want to do is, the easiest way to do this is just to pass to a subsequence a priori where one of these convergences happens along the whole sequence, right? And then you can't make these disjoint subsequences. So a convenient way of writing that is to define the lower Sofic entropy, which is the same thing as before, but with a lim inf. So I'm going to write this h underlined of mu. So let's very quickly, let's write it down. That's the inf over O of the lim inf as n tends to infinity of 1 over Vn log the number of good models. So now what I want to do is, do you recover additivity if you assume that one of your measures has entropy equal to its lower Sofic entropy, which is basically telling you that you get convergence of these numbers along the whole sequence. So let's do the second one. Does h sigma of the product always equal the sum of the h sigmas? Okay, the answer is still no. But now the reason is a little more interesting. Okay, so let me just check. Right, the next thing I want to do is show you the example where this is the case. I'm going to show you an example where on this side you're going to get 0 plus 0, and on that side you'll get minus infinity. You can change it to an example where these are both positive, and on that side you get minus infinity. But let's just do this first. And I'll show you an example where mu equals nu.
Is it important that the bad guy has minus infinity?
We don't really know. That's a very good question. That's, yeah, I'll say more about this later, but we don't really know how many different failures you can see. All the failures we know about right now involve somebody being minus infinity, and it's important to figure out if that's always what happens. Okay, so this example will take a little bit longer, but let me try and do it somewhat carefully. Okay, so first let me write the definition of the system. I have to define the system and the Sofic approximation. I'll start by defining the system for the people who know what co-induction is, and then I'll draw a picture for the people who don't know what co-induction is. Okay, I'm going to take H to be a free group on two generators. H prime is going to be a copy of the same thing with two more generators, and then G will be the free product of those. So that's a free group on four generators. But the subgroup H is going to play a distinguished role as a subgroup of G. And now consider the following trivial H system. So let A is going to be the alphabet 0, 1. Mu 0 is going to be the measure that gives you 3/4 mass on 0 and 1/4 on 1. And T is going to be the trivial action, T naught is going to be the trivial action of H. And I should say the number 3/4 is not very important here. It just mustn't be 0, 1, or a half. So that's the next best thing. Right? And now the whole system.
Excuse me, I feel confused. What is trivial action of H?
Everything is the identity.
Sorry?
Every element of H acts as the identity.
And this is the action of H? Or
This is the action of H. And now I'm going to build the action of G. Is that okay? Okay. So now consider your larger system, which is the co-induction from H to G of this system. Okay, so this co-induction, you can write that as a shift system for G. Let me write it as AG mu S. And now I'll just describe it as a picture for those who can't do co-induction in their head yet. I couldn't until a couple of weeks ago. So what does this do? It's a random coloring. So mu is the law of a random coloring of A to the G, and it's going to be shift invariant. So here's a picture of G. Right? Inside it, there are a lot of right cosets of H. Cosets of H. And now it just picks independently a color for each coset, but then colors the whole coset in that color. So color each coset of H independently according to mu naught. And that is now a shift invariant random coloring of G. Okay, so that's the action. A right coset. For me, H is on the right, so it's sets of that form. Okay, but I haven't told you which side the shift action is on, so. Now you know. Okay. Now you know. I don't know. That's why I didn't tell you. Yes, that's right. So what I want is that if you have this coloring and you look at the color at the identity, then applying the subgroup H doesn't change it. Okay, so that's the key feature. So color at the identity is H invariant. So this is an example of a co-induced action. Very often, if you just choose the Sofic approximation blindly, these will give you Sofic entropy minus infinity, but I'm going to show you a Sofic approximation that does give you models for this, and the Sofic entropy will be 0.
So wait, just to confuse me. That's the usual shift, but the measure is supported on...
Yeah, it's the usual shift, but the measure is generated this way. That's right. It's not just IID. If you think that's simpler, then you're welcome to write it that way. Yeah, you're welcome to write it that way. That's fine. Okay, not in my head, but okay. All right. So now I have to tell you what the Sofic approximation is. So this will also be generated at random, and I will show that, I'll argue that with high probability, the Sofic approximation I give you has the properties I want. So to generate the Sofic approximation sigma n, I need to tell you what the four generators do. Sigma n of A, sigma n of B, sigma n A prime and sigma n of B prime on some set Vn, and then for any other group element you just multiply the corresponding word and that will tell you what sigma n of the group element is. So I'm really just drawing the Cayley graph picture. So I'm going to look at Vn's of size multiples of 4, and each one I'm going to break into two subsets, which are the values 1 through 3n and then the remainder. And let's call that subset un and that subset wn. Okay? Now, for these two generators, just choose uniformly at random two permutations of the whole thing. Independent and uniform from the symmetric group of Vn. And for these two, you also make an independent uniform choice, but only from those permutations that respect this partition. So really you're choosing a pair of permutations within here and a pair of permutations within here. So now choose uniformly, independently from the subgroup of those Tor in the full symmetric group such that Tor of un equals un. So nobody can cross from one side to the other under these two. Okay, and those are going to generate your Sofic approximation. All right. So now what would it mean for this Sofic approximation to have a good model for the original system? Well, it means that would be a coloring, a 0-1 coloring, so 0-1 to the Vn, such that for a typical vertex, if you move using h, the value doesn't change. But if you move in any other direction, it does with probability whatever it should be for the IID law. So A has to be approximately invariant under sigma NA and sigma NB. Okay? And then it has to have the right statistics for moving in other directions. Let's worry less about that. So is there such a coloring? Well, yes, you put a 0 there and a 1 there. Are there any others? Well, no, not really. That's just about the only one. So e.g., A could equal the indicator function of Wn. And then you can check the statistics for moving by other group elements, and if you chose the sigma n's all at random, then they work out too. Okay, so that's a good model for this group action on that Sofic approximation, but it's also roughly the only one because, and let me just say this in words, and if you don't know what an expander is, then don't worry about this part. Within UN, the action of the subgroup H is given by two independently chosen partitions. So the graph it generates is an expander. What that means is that within UN, you can't cut that set into two more substantial pieces that are roughly H invariant. And within WN, you can't cut it into two more pieces that are roughly H invariant. That means if you want to cut the whole of Vn into two H invariant pieces, you have to use that partition, up to some small errors here and there. Okay, so expansion properties within each of Un and Vn give that this is effectively the only good model. So by expansion of, let me just say this sloppily, of sigma Na and sigma NB within UN and WN, any good model is close to A. And close really means here close in the Hamming distance. So there are a few errors. Okay, so there are good models, but not very many. There's just that one, basically. So the Sofic entropy is 0, right? That's obvious if you're used to doing these calculations in your head. So there are some good models. So the Sofic entropy is at least log of 1, which is 0. But there are exponentially few. So it can't be bigger than 0. So, okay. But now what would it mean to have a good model for mu times mu? Well, that should mean that A is a good model for mu, and B is a good model for mu. But also it should mean that if you look at the pairs AV, BV, as V ranges over the whole of Vn, the frequency with which you see 0, 1 should be roughly 1/4 times 3/4. So among these pairs should see 0, 1 roughly, say, 3/16 of the time. But hang on, if A and B are both good models for mu, then they're both close to that one cut. So they're very close to each other. So you almost always see 0, 0, or 1, 1. They're almost always the same. So that's impossible. Does that make sense? That's a contradiction. So there are no good models for the product, and h sigma of mu times mu is minus infinity. The problem with choosing 1/2 is that then I can flip it over. I can have 0, 1, and 1, 0. So actually with 1/2, what you find is that h sigma of mu is 0, h sigma of mu times mu is 0, and then h sigma of mu times mu is minus infinity. That's the problem with a half. Okay. Right, so this can happen. It can happen that there are good models for both of your factor processes, but you can't combine any of them into a good model for the whole process. And so now I want to tell you what we can say instead. Okay? So the hope... Yes? Well, that's for G, that's ergodic. It's only not ergodic for the subgroup H. You can do it, I'm pretty sure you can do it with H ergodic, but the analysis gets messier. You take something like one of these very slowly changing Markov processes for H, and that will still work. But it's an extra batch of epsilons in the middles. Okay, so the hope is to find the following. I want some formula. So if I'm always going to assume I have this stability that I don't need to pass to disjoint subsequences for the two Sofic entropies. So I'm always going to assume that. And then I want to know, can you have some lower bound on the Sofic entropy of the product? No. So that's Sofic entropy of nu plus some other function that only depends on mu. Can you do something? And the answer is yes, and now I'm going to tell you what the other function is. Okay, yes. So at this point, let me digress a little bit. I'm going to define this other function in 2 steps. There'll be an improved candidate that still doesn't work, and then there'll be the true thing that does work. Okay? But I'm going to take a little bit of a meandering course to get to this guy. So the next thing I want to talk about is measures on the spaces of models. And at this point, I'm overlapping with the last part of Lewis's talk and also with Miklosh's talk. So this is now the river is going like this. Okay. So let's suppose you have your Sofic approximation. You have your shift invariant measure. And now I'm saying something that I know is similar to what was in Miklosh's talk, but I actually had to miss that one, so I can't remember his notation either. But let's consider a sequence of probability measures on these finite sets A to the Vn. Okay? And I'm going to define some senses in which these mu-n's can converge to the measure mu on the full shift space. If I can find, there it is. Okay. So I'm actually going to give you 3 different kinds of convergence. They are progressively strong, but they are closely related, so we'll see that. So I say that mu-n converges locally weak star to mu if for any weak star neighborhood of mu, weak star open containing mu, it eventually holds that most of the marginals of this guy around the vertices in Vn resemble the corresponding marginal of mu. So what do I want to say? I want to say that So if you just remember our picture, for a moment I had this picture of what Vn looks like. For most vertices in Vn, the graph around them looks like a copy of the Cayley graph. I now have a measure μn on colorings of this guy. This, remember I told you I originally had a finite window and I threw it away from the notation, but imagine there's a finite window in your head W. Maybe we put that there. Then what you're doing is picking a vertex V, looking at the marginal of μn, that's just colorings of the corresponding patch of W, not the whole thing. And you're asking that that coloring of W should be close to what mu itself does for most V's. This is called local weak star convergence. I should add that this is not my definition at all. This has already been in the statistical physics literature for a while, but because they are more purely probabilists than I am, they call it local weak convergence. But okay, that's fine. So let's define that. And now right away I want to add an extra condition, and this will be my next notion of convergence. So I will say that μn quenched converges to mu if this local property is true, but also μn is asymptotically supported on individual good models. So for any O, as usual, O is the weak star neighborhood of mu, you get that μn of the set of O good models tends to 1 as n tends to infinity. So there's two different kinds of approximation, two different ways in which you can see approximations to mu coming up here, right? This is saying that the marginals of μn itself resemble mu. This is saying that μn is mostly supported on single points whose empirical distribution resembles mu. Okay, so there's two different kinds of approximation, and I'm asking for both of them. Yeah. Yeah, so that's right. If you choose coloring from μn, then with high probability you get a good model in the previous sense. That's right. So I think in Miklich's talk he talked about random good models. μn is the law of a random good model if it satisfies this. Okay, that's the connection. So this is obviously stronger than local weak star convergence, but here's a fact, it's not too hard to prove, but I won't dwell on it. If the thing you're limiting to is ergodic, then they're actually the same. Then this one implies this one. So 1 implies 2 if mu is ergodic. Not an if and only if, though. You can have non-ergodic processes that have sequences like this. I'm not going to dwell on this, but I will say it's important that I'm allowing non-ergodicity here, and you'll see why shortly. Okay? So it's important that I have a story to tell even when mu is not ergodic. Okay. So one reason for introducing this is that you would like to come up with a substitute for Sofic entropy that does behave well under Cartesian products, and then maybe that will give you some insight into the original problem. So here's an attempt at such a substitute. Instead of counting good models, let's look at the effective number of good models that you can see using such a sequence of measures μn. Okay, so let me give you a couple definitions that reflect that. So first, for epsilon positive, I'm going to write curve epsilon of μn for the least number of points you need to cover more than 1 minus epsilon of the measure. Okay, so it's the effective size of the support of μn, where you allow yourself to throw epsilon of it away. And now I can make a new notion of entropy where, instead of counting all the good models, I ask for the fastest growth rate of these numbers that I can get along a sequence of convergent measures. Right? So I'm asking effectively for sets of good models that aren't just sets of good models, they support measures in this sense. Okay, so I haven't told you yet why I might do that, but let me write it down. So the Q stands for quenched. This is a little bit of a mouthful, but in ways that are fairly easy to understand why they're there. Okay, so the first thing I have to remark is that whether you can find such a sequence of measurements or not depends on the Sofic approximation. All of this depends on our initial choice of the Sofic approximation. And it could be that for your full Sofic approximation, you just can't find a sequence of measures that converges, but you can along some subsequence. And in that case, just as with Sofic entropy itself, I want to be able to pick up values from that subsequence. So in the definition, this outer supremum lets me choose an arbitrary subsequence of the Sofic approximation, and then ask for measures on model spaces that just converge along that, and not worry about what happens at the other times. So the outer sup is just over a choice of subsequences, and then a choice of measures converging along the subsequence. And then for those, you do basically the same as you did for Sofic entropy, except now you count the lim sup of the exponential growth sizes of these covering numbers, rather than the model spaces themselves. Okay, so that's the definition. First obvious fact is because the model spaces do asymptotically support the mu-n's, the covering numbers are eventually less than the sizes of these, or perhaps equal. So this is always smaller than Sofic entropy, or perhaps the same. So always you have HQ sigma mu is at most H sigma of mu, and that's just because of property 2. And now when you come into this, you might hope that, now this is a Sofic entropy notion that does behave well under Cartesian products. And you might think that because now if I have these sequences of measures mu n, let's say along the whole Sofic approximation, in general it would be a subsequence. Suppose you have these mu n's converging to mu. Maybe that means that mu n times mu n converges to mu times mu, and then I would be happy, because I just have to estimate the support of mu n times mu n. So the question now is, does mu n quenched converging to mu imply that mu n times mu n quenched converges to mu times mu? Well, for local weak star convergence, this is true. So if most marginals of mu n are correct, then most marginals of mu n times mu n are just the marginal of mu times mu. That's easy. So true for local weak star convergence. But unfortunately for quenched convergence, this is false. But not true for quenched convergence. And now you can see why I needed to have a story to tell when the system is not ergodic. It's because if mu is ergodic, its product doesn't have to be. So if mu is weakly mixing, then yes. If mu is weakly mixing, then we're happy. Mu n converging to mu implies mu n times mu n converges to mu times mu, and entropy will be additive. So this is a lemma along the way to the true answer. If mu is weakly mixing, then mu n quenched converging to mu implies that mu n times mu n quenched converges to mu times mu, and the quenched model measure Sofic entropy of the square is just twice the value for mu itself. So in that case, we're happy. But okay, we don't want to only work with weakly mixing systems, so what can we do to fix this? Well, the fix is actually very cheap. All I do is I go back to this definition, and I insist on convergence of the squares here. I just build that into the definition, and I call that doubly quenched convergence.
And this can be far away from weak mixing.
Sorry?
The double condition still will be range of space away from weak mixing.
Well, let me tell the story, and then maybe we can come back to your question. So this holds if mu n times mu n quenched converges to mu times mu. Okay? So that's a very cheap thing to say. Let's just build that in. And now, happily, I'm back at exactly the board that I wanted. And let's do that. Okay. So now let me tell you some things that happen. So you should think of doubly quenched convergence as some kind of analog at the level of Sofic approximations of weak mixing itself. Okay? So in particular, if mu is weakly mixing, then these notions are all the same. Then local weak star convergence implies quenched convergence implies doubly quenched convergence. There's no difference for any of these. Okay? But there are also analogues in the theorems you can prove about doubly quenched convergence. And here's an example that gives you a flavor of the results. If mu n doubly quenched converges to mu, and nu n quenched converges to nu, then the product works out. Just as if mu times mu is ergodic, then mu times any other ergodic system is also ergodic. Right? So it's a direct analog of that characterization of weak mixing. And then there are others about individual equidistribution that I won't write down for want of time. Okay? But this really does behave like weak mixing in these formal equivalences. And using this, you can now start to read off consequences. So the first one I don't have time to prove for you carefully, but it follows quickly from another characterization that's like weak mixing. The first consequence is this. If H sigma of nu is equal to its lower entropy, so it's quenched at the level of the product. So mu n times mu n, quench converges to mu times mu. So if nu has entropy equal to lower entropy, then the entropy of the product is always at least the entropy of nu plus H dq. So you can always put that number there. That's theorem 1. Theorem 2, in some way perhaps is less interesting, but it's worth recording. That one really is truly additive. Again, you have to make an assumption like this, but then it's truly additive. So if H dq of nu equals lower H dq of nu, I haven't defined lower H dq of nu, but you can go away and guess what it is. You just insist on good behavior along the whole sequence. Then H dq of the product equals the sum of the H dqs. So in this sense, H dq is much more regular than Sofic entropy itself. It does behave well under products. And then the last thing I want to mention, as the time runs out, is that there is a sense in which this theorem is actually best possible. You can't do any better in the question I posed of what can you put here that depends only on mu. So let me just tell you that. So once you understand these measures on model spaces a little bit, you can prove a different formula that's also equal to H dq. So it goes like this. Yeah, so I'm working on a finite alphabet. That's fine. So for any shift system with a finite alphabet, let me write that assumption down explicitly again. We have that H dq of mu is equal to the following. If you start taking Cartesian powers of mu, the entropy doesn't have to grow linearly. It can fall short of that, because we've seen examples where it can go down. But keep taking Cartesian powers and keep taking Cartesian powers, and look at the rate at which that grows. So I'm looking at this sequence of numbers. That's subadditive as a sequence, so it has a well-defined growth rate by Foucault's lemma, and that's actually equal to H dq. So if you like H dq, you can also think of as the stabilization of Sofic entropy undertaking Cartesian powers. And a corollary, very easy corollary, is suppose you have a mu such that this sort of stability property is true for all of its powers. So if H sigma of mu times k equals lower H sigma of mu times k for all k, then that's the best constant you can put in this formula. So then H dq of mu actually equals the inf of the differences H of some product minus H of nu itself, where nu is another process whose upper and lower entropies coincide. So very quickly, why does this imply this? Well, if that's the growth rate of the sequence, then for any epsilon, it happens infinitely often that that number doesn't grow by more than this plus epsilon. So there are infinitely many k where such that h of mu to the k plus 1 is not more than h mu to the k plus h dq plus epsilon. And now rearrange. Let nu be that. Here is your example where the difference got arbitrarily close to HDQ. So this is the lower bound, and this is really the best lower bound you can ask for in general. And now the punchline, which is the open problem for this talk, this whole story goes through just the same for a completely arbitrary G process. What you have to do, instead of using a finite alphabet A, is use some compact metric space, and then you have to count covering numbers rather than individual points, and so there's an extra layer of deltas in there as well. Everything works just fine except this. This one I don't know how to prove except for a finite alphabet. I really hope that it's true in general, but the proof doesn't work in general. So is this true in general? Does something else happen? Are there systems where there's a gap here if you can't find a finite generating partition? And I think that's it. Thank you very much. So if both the measures are weak mixing, you do not necessarily have additivity for H sigma, but you do get it for H sigma Q. So you don't need to go from Q to DQ in that case. But for the original Sofic entropy, no, not necessarily. And there are slightly fancier versions of this example where you can even insist on weak mixing. Probably you can even insist on total weak mixing. For H sigma itself, I don't know of one. No. And you always hit this problem that there can be just that one good model, and then you can't choose pairs. I don't know of a mixing condition that prevents that. Yeah.
You could put a condition just on the Sofic approximation.
You could. Yes. So you can restrict to certain Sofic approximations for which additivity does always hold. And all of these entropy notions coincide. So I think if you take slowly growing, if you start with any Sofic approximation, but then for Vn you replace it with some Cartesian power where the power grows slowly with n, I think that's going to work.
Any example of a real dependence of approximation, when for some claim it's for some approximation is true and for another not true?
Oh yeah, so this example I showed you where H sigma of mu times mu is not twice H sigma of mu. There are different choices of Sofic approximation where it is.
For what group?
Oh, that was the free group on 4 generators. Yeah. And actually, as a general rule, maybe you know better than I do, but the examples I know of where you see different behavior along different Sofic approximations all come from free groups because we know how to build lots of different Sofic approximations for those. There may also be some things where you have lots of choice in a residually finite group. You can use property, yeah, okay. And actually, I skipped over this, but there is an example where HQ is not equal to HDQ, and HQ is not additive, and that is the example I know is a profinite action of a property T group, of a residually finite property T group.
So, just a reminder, so Damian student Carter is just showed you that for higher rank latitude you can study that you can find many actions that don't see each other. But it's also the same term with minus infinity.
Oh, yeah, yeah, so you're getting, right, you just can't build models on one side. Yeah, okay.
It's not clear. That's the other question. It's not clear to me that you cannot build some supermodel.
Right. So, well, some supermodel or some super-Sofic approximation?
By model, I mean Sofic.
Yeah, okay.
So it could happen that for any two process, there exists some godforsaken graph.
It could be.
somewhere
We don't
else
know. Right.
Where both can be modeled. I haven't seen a counterexample for that.
Yeah, no, I haven't either.
Question. So I have one. So is the question entropy equal to the entropy for Bernoulli shift?
Yes, everything is equal for Bernoulli shifts. So for Bernoulli shifts, you just take the product measure to the power Vn, and that doubly quench converges and everything is equal. I don't know conditions other than ones where there is an obvious... So I will tell you, okay, let me just say something about this. There is a generalization of the Bernoulli shift fact, which is that... Where's the thing? Oh. If you start with two infinite groups, so G and H both infinite, you start with any action for G, and then co-induce it to an action of the product group, then this guy, all the entropy notions coincide for product Sofic approximations. And then if G is trivial, that's just the Bernoulli case.
Can you say some kind of jointness statement like
Who knows? It would be nice. I don't know. I think, yeah, it's a nice question. We don't know.